Thank you. Hi everyone. Today I'm going to be talking about randomness beacons and some recent analysis on the MinRoot sequential function. I'm going to start with a disclaimer, being that any opinions that are expressed in this presentation are strictly my own and not in any way reflective of the Ethereum Foundation more generally. I'm going to just start by saying what is a random beacon and how are we using them in Ethereum. So randomness beacons in Ethereum are basically being used because proof of stake requires a good source of randomness. We have a proof of stake algorithm where only the block proposer is allowed to propose new blocks. They kind of fill the role as a leader. There can only be one block proposer at a time, and this block proposer is randomly selected using a good source of randomness from the pool of validators. Later on, other validators can vote on the block. They can say whether they think it's good or bad, but they can't propose the block themselves. This good source of randomness should not be biasable. And in particular, what this means is it means that just using a hash function won't quite do it. So to say more on this, let's suppose that RO is our random function. And what RO is going to look like is we're going to hash some seed and then take the result modulo the total number of validators. But the total number of validators is never going to be, that big. It's never going to be exponentially large. And what this means is that you can brute force find some kind of seed such that RO of the seed is equal to the output that you want it to equal. And now we have a bit of a circular problem going on because we need to choose this seed somehow. We kind of want it to be random. We can't use RO for choosing the initial seed because then that would be circular. And we're in a distributed setting where we don't have any trust parties that we can rely on in order to choose this seed for us. So reminder, the randomness beacon is being used so that we can choose our block proposer. What we want is that at time t, nobody in the world can guess what the randomness is going to be. But at time t+1, everybody knows what the randomness is, and it's verifiable, so we know who the block proposer is. And nobody can nobody can bias the distribution of the beacon, so they can't bias it to get the output that they want it to be. Currently, Ethereum is using the Randall random beacon, and this is a very simple commit reveal scheme. There are 2 rounds. In the first round, the validators are going to commit to their randomness. And this commitment, it's going to be hiding, so nobody can see what the commitment contains. And in particular, validator 2 here is not going to know what R1 is, and validator 1 is not going to know what R2 is. Also, more important for the second round is you cannot lie about the content of these commitments. In the second round, all the validators are going to do is they're going to reveal R1 for validator 1 and R2 for validator 2. And then the actual randomness we're going to have, the thing that's going to determine our seed, is going to be RO of R1 concatenated with R2. So this is a great scheme. It's very simple. It's easy to understand. However, it is biasable. In particular, let's suppose that we have a malicious validator 2. In round 1, they behave completely honestly. They commit to their randomness R2 as they're supposed to. But then in round 2, we have that validator 1 is going to reveal their randomness R1 before validator 2 says anything at all. So validator 2 then knows what R1 is, and they can decide whether to reveal R2 or not. They can't choose any randomness that they want to because they are committed to R2, but they can choose to say nothing at all. And they therefore have 2 choices of random output. So now validator 2 can choose whether they want the final random output to be RO of R1 concatenated with R2, or just RO of R1, and choose which outcome they like better. So this is already a little bit of biasability with just one bad validator. If we have two bad validators who are colluding and happen to sort of talk one after the other, then they have more choices of what they want the random output to be, and therefore who the block proposer should be. So if there are two bad validators, in round 2, they can now reveal R2 and R3, or they can just reveal R2, or they can just reveal R3, or they can reveal nothing at all, giving them 4 choices of output. And this is going to scale very badly as we have more and more bad validators. So, for example, if we have 3 bad validators, they have 8 choices of what they want the randomness to be. And more generally, if we have m bad validators, then they have 2 to the m choices of randomness, and therefore really a lot of choice on what they want the output to be. So this is what we're currently doing. We would like to move to a setting where this isn't a feasible attack and where nobody's able to bias the randomness in these kinds of ways. So there's the question now of what solutions are there? There are sort of 2 well-known solutions for this. One requires threshold signatures, and the other, which is more going to be the topic of this talk, is going to be verifiable delay functions. But I will just talk about threshold signatures first. These have the really good benefit that they actually exist, which is very important in a potential solution. They also have no hardware requirements, which is also really nice. You can just run them on a normal laptop and nothing will go wrong. They're efficient enough to be used in practice, and this is becoming more and more true as people research into them further. But they do have a big kind of fundamental catch, being that there is a trade-off going on between the secrecy and liveness thresholds. So let me say more on that. By secrecy, we mean that TS is the fraction of parties who are bad. If TS fraction of parties are bad, then they can corrupt the randomness in order to get some bad output. Let TL be the fraction of parties that are bad for liveness. If TL fraction of parties are bad, they can stall progress, so they can make it so that no block proposer is determined at all, and therefore no progress is made. And we have a fundamental trade-off going on, which is not to do with our schemes. It is genuinely impossible to have a setting where you have TS plus L summing to more than 1. So what this means is that you cannot have an honest minority for both the secrecy threshold and the liveness threshold. And having honest minority is very important to us, and it is something that we would like to have. Verifiable delay functions, on the other hand, they do allow you to have honest minority. They add an extra factor into the game. We now have time on our side, so to speak, and therefore we're able to get better security guarantees in this respect. They are also efficient enough, but they have 2 catches, one being that, I mean, depending on how you define existence, it's questionable whether they exist. We're trying to make them exist. They also have very challenging hardware requirements, which is something that, you know, we're having to battle with and tackle in a very practical sense. Simpkin also has some upcoming work, who is a member of our team with some others, on a potential time lock solution, which is also going to use timing assumptions. So the first thing I will say is that VDFs are theoretically amazing. They're actually still a fairly new concept. The original idea, I think it was in 2018 actually, rather than 2019, they updated the paper. But the initial idea was to run a snark prover over an iterative hash function. So what this would mean is that your random output, rand, is going to equal a hash of a hash of a hash of a hash, dot, 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 of a hash of a seed. And then in step 2, you're going to reveal this random output, and then you're going to compute a snark proof that rand was actually computed correctly so that anyone can verify that result without them having to compute it for themselves. And the idea here is that if the hash function looks random, then the final output rand is unpredictable. Security is going to be implied by a timing assumption. And the idea here is that if you cannot compute enough hashes in 2 minutes, then you cannot bias rand in 1 minute. So if RAND is determining who our block proposer is going to be, and you have to decide whether you're going to commit a reveal or send any messages within 1 minute, then you couldn't possibly know what the final random output will be within that 1 minute, and therefore you can't bias the result. I would say that there is only one well-ish studied timing assumption, and that is RSA time lock puzzles. This says that it is slow to compute 2 to the power of t modulo n for n some RSA modulus. One thing I will say here is that we're using an RSA modulus, but that does not mean that security is implied by RSA. If you can break RSA, or at least if you can break factoring, you would be able to break these time lock puzzles, but the same is not true. If you can break these time lock puzzles, it does not necessarily imply that you can break factoring. So there were some RSA time lock puzzles that were set 20 years ago, and it took 20 years to solve them, which was faster than was originally expected. And actually, 2 solutions came out in fairly quick succession, but the techniques they were using were completely different. The first solution was faster than expected, basically due to hardware improvements. Hardware got better quicker than the original designers were expecting, and therefore someone that was actually running the standard algorithm on the hardware available was able to find a solution quicker than expected. The second solution is more interesting in the sense that due to algorithmic improvements, they were able to compute the base sequential function quicker than was known how to do in 1996. For VDFs, it really does matter how quickly we can compute our base sequential function, and having speed-ups on the computation time of the base sequential function would matter. Okay, so the good regarding the RSA verifiable delay function is theoretically possible, it's as well studied as we're going to get, and it's probably efficient enough. There are some catches with this, of which I will talk about the first 2 in much more detail. The first is that there is a very challenging trusted setup. There's also very challenging hardware. Also, it is not post-quantum secure, nor is there any way that we know to upgrade it should something go wrong. So for the RSA VDF, we require a trusted setup, basically because we need a shared modulus that nobody in the world can factorize. This creates some long-term parameters, which are creating a single point of failure where if an attack happens, it could go undetected. The trusted setup we're running in order to get this modulus, it is somewhat related to zero-knowledge snarks in the sense that there's a trusted setup, but actually it is way more complicated, which makes the chances of an attack much more likely. But 2020, we were there thinking, we would like to run the RSA VDF, shall we give it a go? Is it really hard? And we investigated a candidate trusted setup for generating RSA moduli. To cut a long story short here, the candidate solution we were looking at was attacked during an audit. And the basic gist of this attack was that there was an unproven and yet very important efficiency optimization that we were relying on, which caused a major bug. And if you look at Omar's talk from RWC 2021, you can see far more details about that. And this attack, it kind of caused us to go back to the drawing board and think, is there a different way in which we can run a VDF? Are there other solutions? But actually, I would say that even if this attack hadn't come out, there's a good chance that we would have been caught with the next issue, which is we were already looking at the hardware for the RSA VDF, and we were already realizing that it was going to be very difficult. So VDF users, they need to have hardware which is not a lot slower than the very best possible hardware for the VDF they're trying to compute. Arguing that you have the best possible hardware is really hard. And if you have very complicated hardware, then it becomes even harder to argue that it's the best possible because there are more places where people can optimize. There are more places where you potentially haven't done things in the best possible way. RSA has a very large modulus, and this large modulus kind of inherently creates very complicated hardware. So after this happened, there was a matter of, okay, back to the drawing board. We know that iterative hash functions or iterative sequential functions could be a potential alternative. Maybe these might have nicer hardware requirements. Maybe these might have nicer setup assumptions. Maybe we can give this a go. One benefit of hindsight, which I will talk about more later, is that collision-resistant hash functions do not necessarily satisfy timing assumptions. The two assumptions are completely orthogonal. But in 2020, there were some, I would say, VDF-friendly sequential functions that were coming out. They were very efficient. They kind of looked quite hash-like in nature, and they include sloth, they include vdo, and they include MinRoot. These are not hash functions, unlike the original VDF paper. Instead, they are sequential functions which are designed to be very quick to compute in hardware. The general idea here is that you're going to take cube roots over a 256-bit field over and over and over and over and over and over again. Security is implied by a timing assumption. And this timing assumption says that no attacker should be able to compute the function more than a constant factor, in our case c equals 2, faster than the reference implementation. And working with these VDF-friendly functions was very nice. They have no trusted setup, they're very efficient, the hardware is relatively easy, and actually most importantly, they're very simple. So being able to see what's going on and have a feel for how it's going to impact your protocol was very easy because the thing we were working with was simple. However, there is a bad side of these, being that they'd only just been proposed, and we do not really know how to evaluate their security. It's not like this is something which we've looked at lots in the past, it's sort of all fairly new to us. We decided to investigate the MinRoot sequential function, basically because it was the fastest. The Nova snark prover was able to keep pace with the MinRoot evaluator, which is very important. That means it's efficient enough to run in practice. The snark prover is not going to cause us any problem. And the solution, it was fast, it was elegant, and most importantly, it was simple. So then we're left with the question of how should we evaluate VDF security? The security notion that we're trying to satisfy here, no attacker can compute the function more than a factor of c equals 2 faster than the reference implementation, is a very challenging security notion. Basically because small constant improvements count as practical attacks. This is very different from other cryptographic constructions. So as a comparison, improving the best possible attack on the collision resistance of SHA-3 by a multiplicative factor of 1,000 would have no real practical consequences. You would pretty much need to have an asymptotic improvement on an attack on SHA-3 if you wanted to see an attack being run in practice. So we have this very challenging security notion that we're wanting to argue about. What means are available to us? Typically when you're thinking cryptography, maybe we can do a security reduction, maybe we can assess known attacks on similar objects, bounties can be quite a good solution, and paying lots of experts to gather in a room and see if they can break it is also a fairly good idea. Security reductions, not really available to us here. Certainly I wouldn't know how to do it. Yeah, we don't know how to write security reductions for VDFs. Assessment of attacks on known objects. I would say that unlike hash functions, we do not have decades of research on attack tools and design patterns for attacking timing assumptions. There is some literature on parallel algorithms, which is fairly relevant, but this is more constructive than trying to attack things. Bounties are certainly a very good idea. A caveat I will say here is that we can't really expect solutions to use the attacking hardware because the attacking hardware could be fairly expensive. So assessing whether the solution is a solution or not would need to be done by hand. Paying lots of experts to gather in a room and seeing if they can break it is actually the option that we decided to go with. So after Eurocrypt this year, we paid lots of experts to gather in a room, gave them a challenge. It turns out they could break it. And The attack is detailed in the public report on the analysis of MinRoot. So I've got a link to the report here. It is on the Cryptography Research website. I will just give a moment in case anyone wants to take a picture of that QR code. Okay, I don't see any cameras, so, oh, 2 seconds. The general idea here is that MinRoot is designed over a 256-bit prime order field. And this was very convenient for us because it means that we have a relatively small modulus, which then means that the hardware is very easy. However, the discrete logarithm problem is so solvable over 256-bit prime order fields using index calculus. The discrete logarithm problem really is only hard if we assume at least a 1024-bit prime order field. I think that might now be 2048, maybe even higher. It's going up all the time. Index calculus is actually the reason that we use elliptic curves, which can be secure with 256 bits because there is no notion of prime generators. However, here we're not using an elliptic curve, we are using a field, and index calculus is very relevant. So using index calculus-like techniques, the general gist is that the computation in a 256-bit field can be achieved using 2 to the 25 processors and 2 to the 40 memory, faster than by using just a single processor. Variations of this attack apply to all known VDF-friendly functions. And yeah, the attack uses index calculus techniques. Some comments on this. The original claim in the MinRoot paper is broken. We did say that sequential function, we did say that using a single processor, you shouldn't be able to do things significantly slower than using lots and lots of parallelization. This is a theoretical attack, meaning that it cannot be run on a laptop. The cost of the memory accesses at the moment is not that well accounted for, so it's fairly hard for us to give you a precise amount of time that the attack would take. There are some unknowns. It is unknown how this attack will improve over time, and it is unknown how much larger the field needs to be, especially considering the fact that the attack might improve over time. A final comment is just that this attack would be very expensive to run. You would need good hardware in order to run it. So our statement regarding the public report on the analysis of MinRoot that we released a couple of months ago was posted on ETH Research. And this was signed by the Ethereum Foundation Cryptography Research Team, and all members of the research team helped in the writing of this statement, sorry. Again, I will just leave that QR link up there for just a second. So in this statement, we publicly disclose the attack. We also discuss some lessons learned from the analysis of the VDF, in that the VDF attack surfaces include that there is a bit of a lack of knowledge about how to analyze VDFs that has to just be included in your attack surface. And the attacks that we would expect to see are different and underexplored compared to attacks on hash functions. We also have that possible slight speed-ups of basic computations via massive parallelism can cause very catastrophic attacks. Our closing statement of this report is that a better understanding of VDFs is essential if we are to continue down this design avenue. At the present, we do not recommend using VDFs within Ethereum. Ongoing research and substantial improvements are important factors in potentially revising our perspective on this topic in the future. And this recommendation is we really had the core protocol in mind. So what now? I'm going to be honest with you, we don't really know. While nobody is currently attacking Randall, to the best of our knowledge, we still would like to have a contingency plan in case this changes. Threshold signatures, they still require an honest majority, either for secrecy or liveness, and further VDF research, such as we would like to see, would require a lot of time and a lot of funding. So we're going to be spending the next couple of months back in the drawing board thinking about it, and I would urge you, outsourcing, if you could get in contact with Antonio Sanso, whose email is on the slide, if you have any ideas about possible solutions which you think would be good for Ethereum. Thank you very much for listening.